Hello everyone. This is question 42 from the Silverberg textbook from assignment 18. There are 3 parts to it, pretty much asking the same thing each time. So I'll go through the full solution for A, but then you guys can do B and C, and I'll just go through the balancing because the other steps will be the same. So in each of these cases, you want to balance the equation, calculate E naught, say whether it's spontaneous, and then determine the value of the equilibrium constant, which is K. So we'll start out with the first one. What it is you have cobalt plus hydronium going to cobalt 2 plus and H2. So we're going to break it out into the 2 half reactions. The first one's nice and simple. We have cobalt going to cobalt 2 plus. So first of all, is this oxidation or reduction, which you have to ask yourself. So we are increasing our oxidation state, so that is going to be our oxidation reaction. To balance this, 2 electrons, the thing is that you're releasing electrons, or loss of electrons is oxidation. So the reduction half reaction then is going to be our hydronium going to H2. Now to balance this guy here, well, you know you're obviously in acidic conditions because you have hydronium. First things first though, oxygen. Balance with 1 water, 1 oxygen, 1 water. Now you count up your hydrogens. We have 4 here, 3 here. So that means we need 1 more hydrogen over here. So to balance hydrogens, we can't just add H plus, we have to add an H3O plus balanced with another water. So we need 1 hydronium, and for every hydronium, we add another water. Next comes charge. So I have no charge over here, plus 2 over here, so I need to add 2 electrons. At the stage now we can add these 2 together, 2 electrons in each case. So we don't need to do anything to these reactions in particular, we can just cancel our electrons out. Going to have 2 hydronium, cobalt going to cobalt 2 plus H2 plus 2 waters. Okay, so there's our balanced overall equation. Part of this also asks what E naught of the cell is, which means you need to go and find the reduction half potentials for each of these half reactions using your appendix D in your textbook. So if you go and look for that, what you're going to find is the reduction equation. So cobalt 2 plus going to cobalt, and the number you find from that is minus 0.28, but because we're writing it in the oxidation direction, this is actually going to be plus 0.28 for that one. This reaction here, if you're really familiar, when you have this reduction or reduction of hydrogen to make hydrogen gas, or reduction of a proton, that is the standard hydrogen electrode, which is the potential what all others are based off of. All of them are relative to this one. This one was chosen to be 0. So this makes our E naught of the cell. Adding these 2 together, it's simple, so 0.28 volts. Now the next part of this question asks, is this spontaneous or not? A positive E naught is spontaneous. Remember, this is directly related. This is the negative delta G spontaneous, and a positive E naught is spontaneous. So this one here is spontaneous. And you do also have to find the equilibrium constant. So our equation that involves both E naught and other stuff in there to get to our equilibrium concentration. This one that we looked at in class, RT over ZF ln K, where R is our gas constant, T is our temperature, Z is the number of electrons that were transferred in our balanced equation, Faraday's constant, and then there is K. So we can solve for ln K just by rearranging our equation as such. And all of our numbers, so in here you have E naught of the cell, Z is from the balanced equation, so that's 2. You know Faraday's, 8.314, 298. So in this case here, you should get a number of 21.8. So this gives us K of E to the 21.8, which is equal to approximately 3 times 10 to the 9. So a very spontaneous reaction lies really far in the direction of the products. Now I'll go over the balancing of B and C, but the rest of it would be the same. You'd find E naught, plug it into here, and find K. Okay, what you're given for B okay. So when this one now, split it up. Let's do the easy one first, might as well, which is Br2 going to be our minus. So in order to balance this guy, we need 2 Brs, and they're balancing our charge. We need 2 electrons. Now the next one is a little bit more in depth. So we have manganese 2 plus going to permanganate. First thing, balancing oxygens. So we need to have 4 waters on this side. Now hydrogens, you're told this is an acidic solution. So we have 8 hydrogens on this side. So that means I'm going to have to add 8 hydronium, 8 water to balance out all those extra waters that are in there. 8 hydronium plus 8 waters. So all our elements should be balanced. Now we have the charge, plus 2 total charge on this side, plus 7 on this side. So I need to add 5 electrons over here, which you can also tell how many electrons just based on what's going up here in this case, oxidation reaction. You know, from an oxidation state of plus 2 to over here, it's plus 7. In order to do that, you're releasing 5 electrons. Okay, now is our time to add these 2 together, but obviously we can't cancel out 2 and 5, so you're going to have to multiply by 5, multiply by 2. This makes things pretty full, I guess I should say. So let's start with this one here. We have to multiply this guy by 2. So I have 12 waters. I'm going to make that 24 water. 2 manganese 2 plus, 2 permanganate, 16 hydronium, and 10 electrons. And this other one, I'm going to multiply by 5. So we have 10 electrons, 5 Br2 going to 10 Br minus. Cancel those electrons out. That's the only thing I can cancel out of here. And then put the entire thing together. 4 H2O. So yes, very long equation. Now, in order to do the rest of this one, you'd find your E naught cell. You have to look for these guys in the textbook. I'm just pointing out, when you're looking at the textbook, lots of the equations, when they're balancing, they're not taking into consideration this hydronium. They're just using H plus instead. But H plus doesn't exist by itself. It has to be bound to water. So I'd like you guys to write it as hydronium, which is really what's happening. And you need to balance it with the water. So that's how you're going to find these in the textbook. In this case here, the only other things you need to know for the rest of it is that Z is going to equal 10. You have 10 electrons in your balanced equation up here. And I think you should be good to go with that. Now let's look at the balancing of C. Good. Part C. This type of reaction, where you only have one species that is now becoming two, and the oxidation states are changing, if this is a redox reaction, this is called a disproportionation. So if you look at what your oxidation states are, in this case here, you do have a molecule, well, it's attached together around 2 mercuries, and that overall charge is 2+. So the charge on each mercury is going to be +1. Over here, our oxidation state is +2, and 0. So in this case, one of our mercuries is being oxidized, +2, and the other is being reduced to 0. So those are our 2 half equations. So Hg2 going to Hg2+, that would be our oxidation reaction. In order to balance this guy here, don't forget to balance your elements. That's really what you have here. You don't have any waters and hydrogens to worry about, just the rest of the other elements. And now charges. So we have +2 over here, +4 over here, so we need to have 2 electrons. Other one is our reduction reaction. And here, balancing our mercuries again, and then balancing our electrons. Cancel those guys out simply. And write out our full equation. We can get rid of these coefficients. So it'll just be exactly what was written up top. So that actually was our balanced equation. Then you can go about doing the rest of it, E naught, and finding K from there.